Hello class, welcome back. In this video we are going to start chapter 8 and cover chapter 8 section 1. The basics of hypothesis testing. Basically, hypothesis testing is kind of self-explanatory. You are taking a hypothesis or a claim and then you are going to test that claim using a sample to figure out how accurate that claim is, or can I make that claim? Do I have enough evidence to support it? An example might be, I don't know, 40% of people are jerks. Well, that's probably a bad example because probably more than 40% of people are jerks. But really, that's not a good example because there's no way to actually measure that. A better example might be 40% of people speed every time they drive, or something like that. And then we're going to test that based on empirical data from a sample. So a hypothesis is a claim or a statement about a property of a population. Again, notice that we are dealing with populations because you don't really make hypotheses about samples because you can measure a sample. And then you're using the data from a sample to make inferences about a population. A hypothesis test is a procedure for testing that claim, that hypothesis, about a property of a population. So again, since we are using population, we will use population symbols, mu, omega, and p. So let's just give a conceptual example. So say 1,009 consumers were asked if they are comfortable with having drones deliver their purchases. I don't know, would you guys feel okay with having a drone deliver your Amazon package? I don't know. I don't know if I'm ready for that yet. Anyway, so 1,009 people were asked that question, and 54%, or 545, responded with no. So from this sample, could you make the claim that that p is greater than 0.5? In simpler terms, can you say with certainty that more than half the population, not just a sample, more than half of the entire population is not comfortable with drones delivering their package? So let's talk through this problem for a minute, just using common knowledge and logic to show the need for hypothesis testing. So let's just say that instead of there being 545 people who said no, let's just say 506 people said no, or 50.1% said no. So 50.1% is just barely more than half. So you wouldn't feel comfortable with saying that you're confident that more than half the entire population says no. So 50.1 is not significantly high. Conversely, what if 1,006 people, or 99.7% of the population, said, no, I don't want drones? You would be comfortable saying, okay, that's clearly significantly high. We can say that more than half the population would not want that. But what if you're somewhere in the middle? So this survey that was conducted said 545, or 54% of people, said no. Is this significantly high? I don't know. It may be. That's why we need hypothesis testing. That allows us to answer that key question. It's a lot of steps. In this section, I'll give you a little warning. This section is very wordy. Section 8.1 is the basics of hypothesis testing. And then we will use these basics to actually solve more in-depth problems and examples in section 8.2, 8.3, and 8.4. For the most part, you're going to be following these steps in all of them. This is giving you the basic overview, whereas sections 8.2, 8.3, and 8.4 are going into a more detailed example. So step 1, identify the claim to be tested and express it in symbolic form. Step 2, give the symbolic form that must be true when the original claim is false. Again, that will make more sense, I think, a little bit later. Then you'll go back to the slide and be like, okay, now I know what the heck he's talking about. Step 3. This is where it gets a little bit more meat and potatoes. We need to form two hypotheses. We need to create a null hypothesis, denoted by H0 or H0, and we need to formulate the alternate hypothesis, or alternative hypothesis, denoted by H1. So what the heck does that mean? Okay, a null hypothesis is a statement that the value of a population parameter is equal to some claimed value. So whatever your claim is, you are saying, okay, my null hypothesis is I will set my parameter equal to that claimed value. And parameter, again, could be proportion, mean, or standard deviation. So for now, we'll keep it vague. So we are saying the null hypothesis is saying that whatever we're looking at is equal to that claimed value. The alternative hypothesis is the statement that is saying that the claimed value is different from the null hypothesis. So whereas the null hypothesis uses symbol equal, the alternative hypothesis is saying less than, greater than, or not equal to. It's similar to the concept of a complement we did in Stats 1, where you're saying, okay, if something is this, the complement is that the probability that it is not that. So your null hypothesis and your alternative hypothesis will never overlap in values. It has to be either one or the other. It is either the null hypothesis or it's not the null hypothesis. So let's just do an example to kind of bring this a little bit more clarity to it. I'm a big example professor. I really believe that I can give you all the definitions in the world, but until you see it written out in an example, it's very hard to understand what is actually being talked about. Okay, so a claim was made that the mean age of Middlesex County College students is not 21.2. So the mean age of the sample is not, of the population is not 21.2. So now we want to test this. So we need to make two hypotheses about this statement. The null hypothesis has to contain the symbol equal. So we are saying that the null hypothesis of the population is equal to 21.2. And then if the null hypothesis is equal to 21.2, the alternative hypothesis is saying that no, the mean is not equal to 21.2. Another example, the proportion of students who work is more than 75%. Again, the null hypothesis has to contain the symbol equal. So the null hypothesis is saying that the proportion is equal to the 0.75. And if it's equal to 0.75, the alternative hypothesis, let's go back to the original problem, more than 75. So we're saying the alternative hypothesis is more than 0.75. Step 4. Now we must draw the diagram for the type of curve needed. So think back to chapter 7 when we have normal, we have t, we have chi-square. Next, we need to determine critical regions. And this is similar to concepts we've done in the past, nothing new. So the critical region is the area corresponding to all values of the test statistic that causes us to reject the null hypothesis. We are ultimately looking at the hypotheses here to say, hey, can I reject this null hypothesis or can I not reject it? So we will have to shade the diagram tails based on the symbols used. So we'll have three types of symbols. H1, which is the alternative, can either have a less than, greater than, or not equal to. If we are looking at a greater than symbol, we use the right tail. And you can kind of think of it as an arrow. A greater than symbol kind of is an arrow pointing to the right tail. If H1 contains a less than symbol, use the left tail. And if H1 contains a not equal to symbol, we have to use both tails. Here's another slide just kind of summarizing that. So determine the critical value based on the given value for alpha, which represents the probability of rejecting H naught when H naught is actually true. So what does that mean? Probability of rejecting H naught when H naught is actually true. So if the null hypothesis is actually true, we want to know what critical value will correspond to rejecting that when it will be true. So it's almost like if you have a jury and you are saying that it would be like, sorry, the video got cut off, so hopefully this is a smooth flow. Probability of rejecting H9 when H9 is actually true. Think of it as someone's on trial, and if the defendant was actually innocent, but the jury said that you're guilty, that would be like rejecting H0 when H0 is actually true. So typical values of alpha are 0.1, 0.05, and 0.01, just like we've done in the previous chapters. 0.1 would correspond to an area of 0.9, 0.05 would correspond to an area of 0.95, and 0.01 would be 99% of the total area. So let's look at an example. Use a normal curve and determine the critical value for the following. A right tail test, alpha is equal to 0.05. When I did this, I got a value of 1.645. I encourage you to just look in your textbook to conclude that you can get the same value. And I'll show you my work on the next slide. Okay, normal distribution. We know we're looking at table A2. Alpha is equal to 0.05. Since we are interested in a single test, a right tail test, we are looking for a z-score that corresponds to an area in that tail of 0.05. Remember, table A2, though, gives area to the left of that z-score. Since we are doing a right tail test, we need the area to the right of it. So you can do this one of two ways. You can either use a negative z-score table or the positive z-score table. I think the negative is a little bit easier. So an area of 0.05 corresponds to a z-score of negative 1.645. However, that is for the left tail. Since we want the right tail, don't forget to just make the sign positive. So it will be positive 1.645. Or you can solve it using the positive z-score table. But because we are interested in the right tail, and we have to do 1 minus alpha. So 1 minus alpha is 0.95, which corresponds to a z-score of 1.645. Same answer, two different ways. I would probably do the negative z-score table. Doesn't matter as long as you understand and get the right answer. We'll do another example. Normal curve, determine critical value for a left tail test. Alpha is equal to 0.01. I got negative 2.33. Again, use table A2. Since we are interested in a single tail, we are looking for a z-score that corresponds to an area in that tail of 0.01. Remember, table A2 gives the area to the left. Since this problem is asking for a left tail test, we could read the value directly off the chart as opposed to the extra steps needed in the previous example. So an area of 0.01 roughly corresponds to a z-score of negative 2.33. In actuality, negative 2.33 has a cumulative area of 0.0099, but that's close enough. Again, just make sure that you know how to read table A2 and you're seeing where I got these values, or else you'll be lost in the tests and quizzes. Final example, use a normal curve and determine the critical value for the following. Now we're doing a two-tail test. Alpha is equal to 0.05. So since we are doing a two-tail test, we know that the overall area of the two tails is going to be equal to 0.05. So that would mean that each of the tails, the left and the right tail, is going to be half of 0.05 or 0.025. Therefore, we are looking for z-scores that correspond to an area in each tail of 0.025. So the negative z-score is going to be easier to use. An area of 0.025 corresponds to a z-score of negative 1.96. And as we know, normal distributions are symmetric, so a z-score of positive 1.96 will correspond to a right tail area of 0.025 as well. So your two z-scores are negative and positive 1.96. 5. Identify the test statistic. We are going to identify the test statistic that is relevant to the test. And this is will make much more sense once we are doing sections 8.2, 8.3, and 8.4, but I'll show you what I mean by that. A test statistic is a value used in making a decision about the null hypothesis. So it is what we are actually using to make a test. It is what we're actually going to be comparing the number for. So it is found by converting the sample statistic to a score with the assumption that null hypothesis is true. So you're taking your sample statistic, whether that be your sample proportion, p hat, your sample mean, x naught, or your sample deviation, x, and converting it to a score, such as z, t, or chi. And then we are using that z, that t, or that chi to do the comparison for our hypothesis test. So how do you convert it? What are you doing? You are using these formulas here. These formulas are going to be used really in sections 8.2 and 8.3 and 8.4. Section 8.2 is doing proportions, so we'll be using this test statistic then. Section 8.3 is going to be using mean, hypothesis testing for mean, and section 8.4 is going to be doing hypothesis testing for standard deviation or variances. So here is your formulas for how you are converting your sample statistic into a test statistic. Step 6, we are going to calculate the test statistic based on sample evidence. Again, this chart right here kind of summarizes steps 5 and step 6. There will be two methods that we will be using to do our hypothesis testing. The first is a critical value method. In a hypothesis test, the critical value separates the critical region, where we reject the null hypothesis, from the values of the test statistic that do not lead to the rejection of the null hypothesis. Again, kind of wordy. I do think that you should revisit this video once you look at examples that we do in sections 8.2, 8.3, and 8.4, as that'll really reinforce some of the wordy texts in this section. We will also be doing the p-value method. The p-value method, in a hypothesis test, the p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming that the null hypothesis is true. So when p is less than or equal to alpha, the decision is to reject the null hypothesis. And when p is more than alpha, the decision is to fail to reject the null hypothesis. Finding the p-values, here is a little flow chart to help you do. So kind of start here, follow the test here, and just look at your conclusions over here. If your p-value is lower than your test statistic, you have this condition, and so on and so forth. So kind of follow that flow chart as well. A little note, don't confuse the p-value with the parameter p or the statistic p hat. Just know the difference. P-value is the probability of a test statistic at least as extreme. P is the population proportion. P hat is the sample proportion. Step 7, if the test statistic falls in the shaded region, you are going to reject the null hypothesis. If the test statistic does not fall in the shaded region, then we fail to reject the null hypothesis. So to continue with that, if the p-value is less than or equal to alpha, we will reject H0. Or as the saying goes, if the p is low, the null must go. I don't know, that's just what they told me is a common phrase. And if the p-value is greater than alpha, then we fail to reject the null hypothesis. Let's look at some examples. Say we are doing a right tail test with the critical value of z equals 1.645 and test value of z equals 1.72. So once you have this information, you should be drawing your normal bell-shaped curve, and you have a z value of 1.645, and we are doing a right tail test, meaning we are interested to know if our test value falls in that tail or does not fall in that tail. Since a test value of 1.72 is greater than 1.645, it will fall to the right of that value, or it will fall within that right tail region. Since it falls within that right tail region, our null hypothesis, we can reject it. So because the test value falls within that tail region, we can reject the null hypothesis. Let's look at example 2. Left tail test with a critical value of z equals negative 1.96 and test value of negative 1.25. So you have your bell curve, you have your critical value of 1.96. Left tail test means we're interested to know if it falls within that left tail region. And since the test value of negative 1.25 is greater than negative 1.96, it falls to the right of the value. So it does not fall in the left tail region. Since it does not fall within that left tail region, we fail to reject the null hypothesis. Finally, we have a third example. We are doing a two-tailed test with critical values of z equals positive and negative 2.575, and our test value, we got 2.83. 2.83 is greater than 2.575, meaning it will fall to the right of 2.575. Since it's falling in the right of 2.575, it is landing in the right tail region. So since the test value lands in that region, we can reject the null hypothesis. Step 8, we have to restate that decision from step 7 using simple and non-technical terms. So let's go through the terminology for it. So without using technical terms not understood by most people, we will state a final conclusion that addresses the original claim with wording that can be understood by pretty much your average person. So for help in wording the final conclusion, refer to the table on the next slide or one of the next slides, which lists 4 possible circumstances and their corresponding conclusions. Note that only the first case leads to wording indicating support for the original conclusion. If you want to support some claim, state it in such a way that it becomes the alternative hypothesis, and then hope that the null hypothesis gets rejected. We are mostly interested in the alternative hypothesis, and we are just using the null hypothesis for our comparison to see if we can reject it or not. So wording the final conclusion. So our condition. The original claim does not include equality, and you reject the null hypothesis. Then you would word that there is sufficient evidence to support the claim that blah, blah, blah. And I'm not going to read you the rest of the chart, but you can, on your own time, pause the video and make sure you read that. So, accept or fail to reject. How should we word it when we have the case where it falls within the region? Or fail, should we say that we fail to reject the null hypothesis instead of saying that we accept the null hypothesis? Well, the term accept is misleading because it implies incorrectly that the null hypothesis has been proven, but we can never prove a null hypothesis. And this is an important statement right here. We cannot prove the null hypothesis. We can only reject or fail to reject the null hypothesis. So the phrase fail to reject says more correctly that the available evidence isn't strong enough to warrant rejection of the null hypothesis. Final conclusions can include as many as 3 negative terms. For such confusing conclusions, it is better to restate them to be understandable. Instead of saying there is not sufficient evidence to warrant rejection of the claim of no difference between 0.5 and the population proportion, a better statement would be this: until stronger evidence is obtained, continue to assume that the population proportion is equal to 0.5. So I think a little easier way of using that, as I made this little chart for us to use. So you have 4 possible scenarios. It's almost like a Punnett square from your biology days. Either the claim is the null hypothesis or the claim is actually the alternative hypothesis. And then you can either fail to reject it or you can reject it. So that you have 4 possible outcomes. So if the claim is H naught and we reject H naught, that's the bad case. There is enough evidence to reject the claim that blah, blah, blah. And then so on. You can kind of read how you should formulate your conclusion based on which of the 4 outcomes you have. So the original claim, here's some examples. The average age of a MCC student is not equal to 20.8. And our conclusion was, okay, we are going to reject the null hypothesis. So the formal statement would be, there is enough evidence to support the claim that the average age of MCC students is not equal to 20.8. A second example, the mean age of an MCC student is 20.8. Okay, so notice the difference between the last one and this one. This one is saying not equal to. This one is saying is equal to. and then our conclusion was to reject the null hypothesis, the formal statement would read, there is enough evidence to reject the claim that the average age of an MCC student is 20.8 years. So possible outcomes, similar to your Punnett square before. If you have your H naught is true and you reject it, that's a bad decision because it is true, and then you rejected a true statement. That would be a type 1 error. We're dealing with alpha. Another outcome is the H naught is false and you reject it. Okay, that's a good decision. And then H naught is true and then you fail to reject it. That is a good decision. It is true and you fail to say it's false. And then the final outcome possibility is H naught is false and then you fail to reject it. So it's untrue and then you fail to say that it's untrue. That's a bad decision. We call that a type 2 error. I think a good way of restating this is thinking about a jury. So say someone's on trial. He's on trial for murder. The defendant will always claim he is innocent. The jury has to decide, beyond a reasonable doubt, if the defendant is guilty or not. They may think the defendant is guilty, but if there is not enough evidence, they will have to come back and say he is not guilty. Notice the terminology. They won't ever say he's innocent. They'll just say he's not guilty. It's a similar concept where I can't say you're innocent. I just can't say you're guilty. So I fail to say that you are guilty. And if the defendant was innocent and they called him guilty, ooh, that's a really bad decision. If the defendant was innocent and they said not guilty, good call. Good call, jury. If the defendant was guilty and they said guilty, that's good. And if the defendant was really guilty, but they said he was innocent or not guilty, that's a bad decision. Bad decision, really bad decision. So this is the worst scenario. This is bad, but this is the more detrimental. So talking about those errors again. Type 1 error is the top left box. That's an alpha, which is saying the individual was innocent, but the jury gave him guilty verdict. Type 2 error is saying that you have beta. The individual was guilty, but the jury gave a not guilty verdict. And this is kind of like we were talking about before. So consider the claim that a medical procedure designed to increase the likelihood of a baby girl is effective, so that the probability of a baby girl is P, the population parameter or proportion, is greater than 0.5. Given the following null and alternative hypothesis, write a statement describing a type 1 error and a type 2 error. So type 1 error is the mistake of rejecting a true null hypothesis. Type 2 error is the mistake of failing to reject a null hypothesis when it is false. So the following type 2 error, in reality, P is greater than 0.5, but we fail to support that conclusion. Here is a procedure for hypothesis testing, showing the two different methods that we're actually doing to get to our hypothesis test conclusion. So finally, here's where it all comes together. This is our final example that really should bring everything home. Given the claim that the majority of consumers are uncomfortable with drone delivery, we can apply steps 1, 2, and 3 as follows. This is, again, going back to the original drone example. Step 1, identify the claim to be tested and express it in symbolic form. Using P to denote the probability of selecting a consumer uncomfortable with drone delivery, the claim that the majority is uncomfortable with drone delivery can be expressed in symbolic form as P is greater than 0.5. So given the symbolic form, that must be true when the original claim is false. That's step 2. So if the original claim is P is greater than 0.5, is false, then what's the complement of that? P is less than or equal to 0.5 must be true. Either one of these two statements must be true, because that covers every condition possible. Step 3, we have to create the two hypotheses, the null hypothesis and the alternative hypothesis. So The null hypothesis uses a symbol equal. So we will say that the population parameter is equal to 0.5. The alternative hypothesis is saying that the p-value is greater than 0.5, meaning the majority, more than half. So since the claim p is greater than 0.5 is a claim about the population proportion, we will use a normal distribution, provided that the requirements are satisfied, which they are. So we have a claim made about the population proportion. We have n equals 1009, x equals 545. So we can say that our sample proportion is 0.54, with the null hypothesis equaling 0.5. We can have the assumption that p equals 5, and it follows that q would also be 0.5. So we can evaluate the test statistic using this formula over here that we showed on the chart in between steps 5 and step 6, and we get a corresponding z value of 2.54. Using data from the previous problem, the test statistic is 2.55. I think if you use the computer, you get a slightly different value. We got 2.54, it's fine. And it has a normal distribution area of 0.0054 to its right. So a right-tailed test with test statistic of 2.55 has a p-value of 0.0054. The critical region is shaded in green. The figure shows that with a significance level of 0.05, the critical value of z is 1.645. So here's your critical value of z, 1.645. Our sample proportion is 2.55, corresponding to a p-hat of 0.54. So there is sufficient evidence to support the claim that the majority of consumers are uncomfortable with drone deliveries.